Welcome to the Data Hall YouTube channel. In this video, we are going to talk about the regression assumptions in R. So we are going to discuss how do we test these regression assumptions and what are certain remedies that we can use to solve these issues. So first we are going to install the packages. I have already installed them, so I'm not going to install it in this video. But if you wish to install them, you can use this command. We do install Momentous, ILM test, Sandwich, and car library. These are the libraries that we are going to use for different purposes. For example, we are going to use this Momentous for skewness at kurtosis. Then we are going to use LM test for heteroskedasticity, Sandwich for robustness standard test for robustness standard error to resolve the issue of heteroskedasticity, and then we have this car library which we are going to use for variance inflation factor. So if you want to download this R script or the data that I'm going to use with this video, you can download it from the link given in the description. So let's load the data. We are going to use the auto data. So if I can show you the auto data from the environment, I have minimized the environment. We have 74 observations and 12 variables. Let me show you the data. We have different cars. These are the make of the car, their model, their prices, their mileage per gallon, the number of repairs, and then there is the weight of the car and the length of the car. So what we are going to do is we are going to use certain regression model. So what we are going to use is we are going to take price as the dependent variable and regress it on mileage, weight, and length. So first we are going to test the normality of the residual. For that, we are going to run the regression using LM function, specify the dependent variable, the tilde sign, and then the independent variables, and then the data that I'm going to use. I'm going to use the auto data that I have just loaded. Let me press Ctrl Enter. So the model had been executed, although I cannot see the model in my console because I have to execute the second command, which is summary model. And we can see that we have their coefficient, their standard errors, their t-test, and their R-square and other model fitness values. But what I am interested is in testing the normality of the residual, because one of the assumptions is that the residuals should be normally distributed. So we are not going to test the normality of each of the variable, but we are going to test the normality of the residual by itself. So what we are going to do is we are going to extract the residual from this model. So what we do is we use the resid function and then specify the model that we have created, and this would extract the residual from the model, and we would save these and this new object called residuals. So if I execute this, it would create a vector that would save these residuals. Now what we are going to do is we are going to test the normality of this residual. So we first test the skewness using the skewness kurtosis test. This is coming from the Momentous library. So first we are going to execute the skewness function. Okay, so what we did is we didn't loaded the library. So I'm just going to quickly load all the libraries. Okay, let's get back, press Ctrl Enter. We get the skewness of residuals. Now, ideally for normally distributed data, the skewness should be close to 0. The higher the skewness is from 0, I mean the positive number indicates that it is positively skewed distribution, and a negative number would indicate that it is a negatively distributed skewness. So currently our shape is positively skewed. Let's check kurtosis. Kurtosis should be 3. And now this gives us the kurtosis rather than excess kurtosis. If any test gives you excess kurtosis, then you would have to, then its value should be 0. But in this case, its value should be close to 3. Now we can see that it is somewhat close to 3, right? It isn't exactly 3, but it is somewhat closer to 3. So from that perspective, let's move forward to, now these gives us the skewness and kurtosis, but it isn't a test per se, right? So what we are going to do is we are going to use certain tests. In this case, we have Shapiro-Wilk test. So what we do is we use Shapiro dot test function and utilize it on the residuals that we just created. What we are interested in is the p-value. So if p-value is less than 0.05, then we say that the residuals are not normally distributed, because the null hypothesis of Shapiro-Wilk test is normal distribution, and the alternate hypothesis is that the series is not normally distributed. So in this case, because it is less than 0.05, we reject the null hypothesis in favor of alternate hypothesis, which is that the data is not normally distributed. So from Shapiro-Wilk test, we can see that residuals are not normally distributed. So this assumption is violated. Let's also look at a visualization using QQ-plot. We do QQ norm, and then use the residuals. This would create a QQ plot, but we need a diagonal line that would come from QQ line. Now, the closer the values are to this diagonal line, the more closer this series is to a normal distributed series. But in this case, we can see that it deviates from that line, and so it is not normally distributed. Let's move towards heteroskedasticity. Let's test heteroskedasticity. So first we are going to do Breusch-Pagan test. Now the null hypothesis of Breusch-Pagan test is that the data is that the variants are homoskedastic, whereas the alternate hypothesis is that they are heteroskedastic. So we're going to do BP test and specify the model rather than residuals, right? In the previous assumption, we were testing the normality of residuals, so we used residuals. But in this case, we are going to use model that we have created. Okay, so let's press Control Enter, and it would give us certain values. We are interested in the p-value, and in this case, it is less than 0.05. That means that the data is heteroskedastic. We reject the null hypothesis of homoskedasticity in favor of the alternate hypothesis of heteroskedasticity. Similarly, we have Breusch-Pagan test, Breusch-Godfrey test, and the null and alternate hypothesis of Breusch-Godfrey test is exactly the same as of the Breusch-Pagan test. Again, using Godfrey test, we reject the null hypothesis of homoskedasticity. So now we know that our data is heteroskedastic. So what remedy do we have? Now remember, when the data is heteroskedastic, the coefficients are not biased, but our standard errors are either overestimated or underestimated. So what we are going to do is, let me take the screenshot of this test. So I have taken the screenshot of this test so that we can compare it with the test that we are just going to perform. So what we are going to do is we are going to, the remedy is that we use robust standard error instead of the normal standard error that we get. For that, we are going to use this line of code. Now these two lines of code are combinedly coming from the sandwich library and the LM test library. This coefficient test is coming from the LM test, and then this one is coming from the sandwich library. So if I execute this, it would give me exactly the same coefficient. As you can compare them side by side, they are exactly the same coefficients, but the standard errors are now different, right? So what it would do is it would this robust standard error would just, as the name suggests, would apply a different formula for standard error and adjust standard error for that to cater that issue. So let's move to multicollinearity, and multicollinearity is when our independent variables are correlated. For that, first we check the correlation between our independent variables. I have included the dependent variable, but mainly we are interested in our independent variables. We can see that the weight and length have quite a high correlation. Anything higher than 0.9 would be an indication of a multicollinearity. It isn't a conclusion that there is multicollinearity, but it is just an indication. For more thorough understanding, we should look into the variance inflation factor. So what I do is I use VIF and specify the model. And remember, again, I have to specify the model, and we get these values of variance inflation factor. So anything greater than 10 would specify that there is multicollinearity. Some research papers suggest that it should be greater. Anything greater than 5 would be considered multicollinearity. But anyways, in our case, we can see that there is multicollinearity because the variance inflation factor is greater than 10. So what we do is, one of the remedy, there are multiple remedies, but one of the remedy is that we have to drop one of these multicollinear variables because they present the same information. So what we do is we drop one of them. So in this case, let's drop length and include weight, and let's execute the regression once again and see if the variance inflation factor would resolve. Now you can see that I've executed the model again, and using the new model test statistics, I have executed the variance inflation factor, and I can see that the variance inflation factor has now reduced. So I hope this video was useful. Do subscribe to this channel to stay updated, and do hit the bell icon. Thanks for watching this video.